Very good. We can now move to the next speaker, who is Mr. Fábio Morgado. He's from the University of Strathclyde, and he will be talking about the application of SU2-NEMO to the problem of destructive atmospheric reentry. So thank you very much, Fábio. The floor is yours. 15 minutes. I will give you a notice when you have 2 minutes left.
Thank you, Marco. So, hello everyone. My name is Fábio Morgado. I'm a PhD student from the University of Strathclyde under the supervision of Dr. Marco Fossati. And I'm here today to talk about a little bit about the role and applications of NEMO regarding the simulation of destructive atmospheric entry problems. So, to give a brief outline about my presentation, first I'll talk about the impact that SU2-NEMO can have for atmospheric reentry simulations, and I will discuss 3 test cases that will highlight some of the different aspects that we can find on the reentry problems, and how SU2-NEMO can be used to address them. Then I'll talk about the conceptual study that we performed regarding a TV reentry demonstration case, where all the aspects and topics that will be discussed during this presentation will need to be addressed simultaneously. And then finally, I'll give a brief outlook and the future perspectives of SU2-NEMO for this kind of problems. So the simulation of atmospheric reentry problem is a difficult task because it's an unsteady, high speed and multidisciplinary problem. We have a low number of relevant flight test data to validate, and also it's difficult to make the experiments on ground. And most of the state-of-the-art tools, they use surrogate or engineering models to compute their thermal loads and the structural stress, but this can lead to wrong results because they do not account for the complex flow features that you can find on the flow, such as the shock interface patterns and shock impingement. And this can have an impact on the dynamics of the objects, and also it can have an impact on the overall demise and fragmentation process of the objects during the reentry. So to address this accuracy issue, we can use SU2-NEMO to aid on our computations and simulations. And for those who don't know, SU2-NEMO is a solver that was branched from the standard SU2, but it accounts with finite rate chemistry and accounts with thermal non-equilibrium by using the 2-temperature model by Park. We also performed the linkage between SU2-NEMO and the Mutation++ library, which is developed at Quantum Institute, which allow us to compute custom mixtures, not only air. And this library provides us with the thermodynamics, with the kinetics, and with the support properties of the different species that we want to consider in our flow. So, long story short, so we can use SU2-NEMO to account for high entropy flows with mixtures that can be different than air. So, for instance, we can try to simulate not only Earth's entry, but also Mars or the Neptune entry. And we also can account with the chemical and the thermal non-equilibrium, so account with the chemistry that occurs on the flow. We can also use SU2-NEMO along with a mesh adaptation tool to try to capture the complex flow feature that we can find on our flows due to complex flow features that can appear due to the complex geometries that we are simulating, or to the presence of multiple objects that are next to each other. And then by integrating SU2-NEMO into an external framework that has been developed for this whole purpose of doing atmospheric problems, and I'll discuss a little bit further on the next slides. We can also use SU2-NEMO to try to give us a more accurate dynamic propagation when we have multiple body simulations. So to assess the computational accuracy of NEMO when there is non-equilibrium chemical processes occurring, we have conducted the HYNECC case, which consists on a hypersonic flow of around Mach 9 over a single cylinder, using the parameters that you can see on the table of the slide. So we have adapted the mesh 2 times in order to obtain a grid converged solution, and we adapted it using the metric-based anisotropic mesh adaptation tool called AMG, which was developed at INRIA. And this allows us to obtain stretch elements on the location of the highly directional flow features in order to try to capture them better. On the top of the slides, I present the pressure and the heat flux profiles. So pressure at the left and heat flux on the right, and the results that obtained with SU2-NEMO are with using an orange color. So on the left, we can see that we are pretty much matching the experimental data, while on the right, we are under-predicting the experimental data because we are assuming, for this case, we assumed a non-catalytic wall, although we are still matching the other simulations that also assume non-catalytic walls, such as the no simulations of non-Pellis or of Andrea Lani. And also further validation of SU2-NEMO has been done by our working group, such as Jacob Niels, that has performed already implemented the boundary wall to account with catholicity, but I still need to rerun this case to account for that boundary condition. And also the work of Wally. And more works can be found in the literature that I'll provide at the end of this presentation. So now to assess how good SU2-NEMO can capture the complex flow features, we have conducted this two-sphere case. And we can see that shock interaction is an important phenomenon to capture because it can have a huge impact on the reentry simulations, because the interaction can lead to highly localized pressure and thermal loads on the downstream sphere for this instance that will then affect the overall dynamics and also the demise process. So for this case, we can see that the shock interference will occur due to the positioning of the spheres for a Mach 7 flow. To achieve a grid converged solution, we performed 3 adaptation levels. You can see on the top left GIF, using the same tool AMG to obtain the capture the reactional flow features and try to get more into detail regarding the shock interaction pattern that occurs next to the sphere most downstream. And on the bottom left, you can see the pressure contours regarding the different levels of the grid, and as we obtain a grid converged solution. You can also see that the peak is already due to the influence of the shock impingement that happens next to on the secondary sphere. Then on the right, I give an overview of the Schlieren images. So I compared the experimental Schlieren against the numerical Schlieren that obtained using SU2-NEMO, and the numerical Schlieren is the one with the green color, and we are matching pretty well the experimental data, which gives us more confidence on the results that we got with NEMO. Then SU2-NEMO is also an essential tool for us to analyze the fragment dispersion due to the shock interference, because they cannot be captured using low fidelity models. So to demonstrate this aspect, we analyze the dynamics on this shock impinged ring. So this ring is basically impinged by the shock which is generated by the cylinder, as you can see on the top left schematic, which was the experimental schematic that was used for this test case. It was run at the von Karman Institute. So the ring was placed upstream of the cylinder, which was pulled using a thin wire that they rupture after the startup of the flow at around 3.8 milliseconds. And we have the experimental data available from that time window until 30 milliseconds, but we only simulated until 11.4. And on this time window, we can see the free stream flow at the bottom left, which is unsteady. So to account the dynamics, to increase the accuracy in the dynamics, we have integrated SU2-NEMO into a framework called Titan. And Titan stands for Transatmospheric Flight Simulation, and is basically an external framework that we developed in Python to try to address these reentry problems in a multi-fidelity manner. So Titan uses a quasi-steady approach, and this means that when you give a time window, we can split that time window into several intervals, and for each interval, we consider a steady state of the flow. So for each interval, we run the flow, we compute the loads, and then we propagate in time using Titan. So as you can see on the flow charts, basically Titan is able to generate using an automatic mesh generation tool such as GMesh. We can generate the mesh, we can provide the mesh to SU2-NEMO, which then proceeds with the simulation, and we proceed with the grid adaptation until the grid convergence is achieved. And then we can compute the forces, and then Titan propagates the solution in time to compute the dynamics. And then more information about Titan and also regarding this test case can be found at the literature at the bottom of this slide. So these are the results that we obtained. So on the top left, on the top plot, we check respectively the exposition of the ring comparing the experimental and the numerical. On the middle, the Y position, and on the right, we compare the angle of attack. And you can see that we are pretty matching quite closely the experimental data, having a maximum error for the exposition of 0.6 millimeters, for the Y position of 1.2 millimeters, and for the angle of only 0.3 degrees. Then for the bottom left, I compare the GIF compares the numerical and the experimental Schlieren, and we still are relatively close with the experimental data. For the middle, I just plotted the MAC contours, and for the right, then I have the pressure contours of this case. Then for this final case, I want to present this ATV simulation that was provided us by ESA, and this basically to highlight the role of SU2-NEMO in the simulations of the atmospheric re-entry when coupled within this Titan framework. And on this case, we have to address all the three aspects that I've been referring to on this presentation simultaneously. So the initial conditions are that we want to run at an altitude of 120 kilometers with a relative speed of 7.5 kilometers per second, which corresponds around Mach 28, a phi pet angle of minus 1.5 degrees, and an initial pitch so that our mesh or satellite can rotate of 10 degrees per second. Now, we also assume that at 92 kilometers, we are going to trigger a fragmentation of the main joints that connecting the main body and the solar arrays, as you can see on the left figure. Now, we are only going to use SU2-NEMO when we have multiple objects. So between this 120 kilometers and 90 kilometers, we're going to use Titan. And then after that, we're going to use SU2-NEMO because we already have multi-objects, and we want to assess the interference between the different objects and the shock waves that are generated by them. Then on the right, the bottom right plot, I just show the trajectory plots regarding this window of 120 kilometers and 90 kilometers that was computed by Titan. So Titan basically on this time window uses a low fidelity approach, which is based on the modified Newtonian theory to compute the pressure loss. As you can see on the left, it shows the dynamics from a time step of 0.25 milliseconds up to fragmentation. And you can see the pressure, but you can also see the back phase culling occurring, which is when the body is hidden because of the flow because of the panels. And then on the right, I show our simulation with NEMO, and for the moment it's still an ongoing simulation. I just have still 5 time steps. But this is basically what SU2-NEMO integrated with our framework can do. Is to assess the dynamic of the different objects individually, and you can already assess that on the bottom right panel, there's still already going some influence regarding the shock wave that you can capture using SU2-NEMO that's affecting the dynamics of that bottom right panel. So let's just give a bit of lots of perspectives. We can use then SU2-NEMO for the 3 topics that have been discussed on this presentation, such as to compute the physics of the high enthalpy flows, which we can then account for the chemistry and for the non-thermal equilibrium. When coupled with mesh adaptation, we can capture the complex shock risk patterns that can have an impact on the dynamics and on the demise process. And we can also increase the fidelity of our atmospheric re-entry tools by using this Titan, which is basically multi-fidelity methods that tries to improve and decrease the confidence on the ready state of the art tools that exists. As a roadmap of SU2-NEMO regarding this kind of problems, we just want to increase the robustness of the codes, so we can basically run SU2-NEMO on Titan without any manually setting up the things, so fully automatic. We want to go for state-to-state modeling to improve the chemistry going on. To include the unsteady mesh adaptation, so we can also not only use the quasi-steady approach they are using, but also account for the unsteadiness of the flow. and then to go for ablative surface boundary conditions, we can also account for ablation of the material. And also, I would like to thank some of people, such as Professor Thierry Magin and Miguel from the Rukami Institute, because they helped us on the linkage between mutation plus and SU2-NEMO and gives us some insight about the chemistry. To Adenosyl, because of the IMG code in Irian, gives us the tools to work on our mesh mutation tool for these kind of simulations, and also to the NEMO working groups, such as Jacob and Wally, that have been working tirelessly to develop NEMO. To Carl and to Osgur for their insights as well, and to Katerina also for their work in our code. And then to Dr. Christina and to Dr. Guilherme, because they are funding my PhD and for my project, which is developing this framework tool for the reentry problem. And then here you can find some of the NEMO NEMO simulations that have been done in the literature. So if you have any curiosity, you can just check this list and please suit yourself. And I finalize my presentation. Thank you for your attention. And if you have any questions, please let me know.
Okay, we have some time for questions. Anyone from the audience? Yes, please.
Thank you so much. It was very. I was just wondering the kind of simulation you showed right now. You said how long did it take for the simulation?
I mean, just the NEMO part.
Okay, maybe let me just repeat the question for the people online. Yes, so the question is referring to the simulation on the satellite re-entry, and the question was related to how much computational cost it took running that simulation.
So I can say that for that simulation, I run two adaptation levels, and for each time step, it took me around between 12 and 16 hours on 120 cores. For that GIF specifically, it took around 3 days.
What is the total number of nodes?
The total number of nodes, yeah, I believe it's around 2 to 3 million nodes.
Okay, thank you. Any other questions by anyone? Tom, please.
So I have a question for you related to AMG. So what's the interaction like right now with the AMG tools for doing mesh adaptation? Like, how does it work, in practice between NEMO and AMG?
So for instance, I will give you the example of Titan. So what you can do is that I simulate SU2-NEMO, then I retrieve the solution, and I have this kind of script that I give the solution to AMG, and it basically can generate that mesh, the adapted mesh that follows the highly flow features due to calculation of the metric of the error. And then it also automatically interpolates. And what I do in my script is that after it interpolates, then I can restart the simulation with the new restart file and the new mesh. So in an automatic manner.
So if I can maybe add, so the story is that right now it is not fully integrated inside NEMO. There is a little bit of external scripting, juggling files, but it seems to work.
I mean, it's arguable that it could probably stay. I mean, it might stay that way forever. I mean, maybe we can improve how we do I/O or something, but it doesn't make sense always to tightly couple everything. So I'm just curious how you guys have it right now. So yeah, we should think about it more if you have plans on that. I'm sure people here would be very interested to talk to get to AMG available in other places.
Very sure. Thank you, Tom.